Dielectric and electrical properties of polyetherketone silica nanocomposite for high performance electronic application. I am currently working as lecturer in Dr. SNSS Gandhi College of Engineering and Technology, Surat, Gujarat, India. So the problem statement is epoxy and e-glass composites have highest continuous temperature and high coefficient of thermal expansion, which because of the, and also contain 15 to 20% of bromine, and the ceramic materials which are used as reinforcement in the polymer matrix like PTFE, polytetrafluoroethane and e-glass have higher coefficient of thermal expansion and poor mechanical properties because of their adhesion of fibers and matrix. To overcome this limitation and best of our knowledge, we have used nanosilica, the ceramic reinforcement in the polymer matrix as a reinforcement for electronic application. And there has been some work reported on silica SiO2 at the micron level for intrinsic properties, but in detail it has not been discussed. So the objective of like our presentation is to prepare a high performance polymer matrix nanocomposite containing nanosilica dispersion using hot compaction molding. And then after that, study the thermal properties, TGA, DSC, thermal conductivity, micro hardness, dynamic mechanical and dielectric properties for the PMC, PMNMC produced. So this is the methodology which is used. The selection of material will have polyetherketone, which is the matrix material, polymer matrix, and reinforcement is nanosilica powder. We have taken different composition 0, 5, 10, 20, 30. First of all, we will do the ball milling 10 to 1 ball to powder ratio for 250 RPM for 5 hours. And then after the powder is produced, we will go for the vacuum drying if the moisture is left in powder, and then we'll go for the hot compaction at the temperature 45 megapascal pressure and temperature 380 plus or minus 5, like above the TG, and the dwell time is 30 minutes. And then the pellets are produced, and different pellets according to the different properties we have produced for all set of the samples from 5, 10, 20, 30 we have done, and the powder characterization is also carried out. This is the schematic figure, the vacuum oven used for drying of the powder. This is the ball mill pulverized set which was used for the ball milling purpose. We have calculated the weight percentage and the volume percentage of according to the rule of Mishra formula. So according to the composition, the weight percentage and volume percentage of the reinforcement is varying, and according to the size of the sample we have taken the powder weight which was required according to the formula which is used. And this is the hot compaction which we use to make the pellets. And now directly I'll come to the results. The micro hardness, as we can see, it has linearly increased from NS0 to NS30 for load time of 50 gram and dwell time of 10 seconds. So for NS0 to NS30, we can see increase in the micro hardness from 36.93 for the pure one to NS30 we see 56.07. We have also compared this hardness with another authors work particularly for PEG and other nano reinforcement, and we can see for our work the reinforcement of 20% volume, the micro hardness has increased to 56.07 mm. The thermal properties also we see from the TG and DTG curve that at 560 degree it is not degrading till the 550 degree, and the addition of Si2 has not caused any insignificant change in the melting temperature, and the crystallization of PEG SiO2 composite delayed with increasing SiO2 content. The DMA properties is very important properties. The E dash of the NS30 enhanced by 106% at 50 degree, we can say at room temperature, and at 216 degrees, which is tremendously huge at 250 degrees, then the neat peak. And you can see from NS0 to NS30, the storage modulus for different temperature, the GPA and the range, it has been increased. So the storage modulus of PEG as nanocomposite at different temperature, and the values in the parenthesis is shown in the increase in the net peak. The electrical properties, the volume resistivity of net peak is in 4 into 10 to the power 10 centimeter, which is decreased to 2 power nanocomposite. An insignificant change is seen, and the experimental volume resistivity is of the 2 orders of magnitude higher than critical resistivity, which is used for FR4, the material which is used, fire retardant property 4, 10 to the power 9, we are getting more than that. Thus, the developed nanocomposite have potential use in the applications such as PCBs, circuit board, printed circuit board, electronic substrate, and thermal management. Same way, the dielectric constant over the range of the PEC and nanocomposite decreases slightly. However, compared to net peak, all the nanocomposite exhibit a slightly higher dielectric constant for the frequency range, as seen in the figure. The dissipation factor exhibited, it is over below 0.006 over the studied frequency range. However, just for NS30, it was found to be 0.009. So I'll come to the summary. So all the properties for which we can compare with commercially used FR4 and polyglide. FR4 is fire retardant 4, which is commercially used for the electronic application. Our NS20 and NS30 samples, the density you can see, the CT below TG is also 40.92, CT above TG is 130, thermal conductivity has increased, micro hardness has increased, storage modulus has increased, dielectric constant has increased, and dissipation factor is also increased. So from the above summary, it is observed NS30 offers better properties and hence better for electronic application other than FR4. And here is my conclusion that additionally, this peak Si2 nanocomposite exhibited a remarkably high thermal stability, more than 560, which we saw in the graph. It was not getting decomposed, and significantly surpassing the reported value of FR4, which is 316 degrees centigrade. In comparison to pure PEC, the PEC nanocomposite thermal stability and char yield were both improved. Out of plane measurement of linearity were found to be reduced, which is about 30% less than the linearity of pure PEC, which is a very important property which we have found out. Micro hardness was found increasing linearly. The nanocomposite storage and loss modulus is also found to be increased. Conductivity of nanocomposite increased significantly. And additional to that, a minimum increase in the dielectric constant and dissipation factor less than 0.06 with high volume resistivity makes such nanocomposite excellent futuristic high performance material for electronic packaging substrate and PCB application, that is our printed circuit board application. Any questions?
Thank you, Dr. Joshi. Excellent talk, and you finished well before your time. So if there are any questions, we can
Okay,
take
sir.
them.
Yeah,
Yeah.
we can take if any question. Thank you.